we have a beautiful positive cubic, right? How do we know it's positive? Well, the maximum is to the left of the minimum. In other words, it increases, it decreases, then it increases. So this is a positive cubic. For example, x cubed. Right, that isn't this equation, but just as an example. Now, the question is asking us to sketch the gradient function, f prime of x. So we are given the original function as a positive cubic, so we know the derivative, right? When we differentiate, we will get a positive quadratic, something like x squared. Cool. Alright, so we know where we're heading. We know when we differentiate a cubic, a positive cubic, we get a positive quadratic, for example, something like so. However, we need to know where to position our quadratic in our sketch. So let's look for a few key points. So looking at the cubic, the key points to focus on initially are the maximum and the minimum, because the gradient at the maximum and the gradient at the minimum is 0. Right? The gradient of a turning point is 0. So on our gradient function, which tells us the gradient for any x value, at those particular x values, right, of the turning points, we will be on the x-axis because our gradient will be 0 for those points. So since it's on the same scale, if you get out your ruler, and then you can drop a vertical line. So let's focus on the minimum first. So looking at that, minimum's here, it comes down. Oh, these aren't quite in line, are they? That's not very good. So let's count the squares instead. So 1, 2, 3, 4, 5, 6. So it's just before the 7th square. 1, 2, 3, 4, 5, 6. Just before the 7th. So somewhere in between the 6th and the 7th would be 2, 4, 6. Will be the x-intercept of our gradient function. That is because the gradient, when x equals like 6.5, on the original function is 0. Okay, now we can do the same for the maximum point. So counting the squares again, 1 between the second and third line. So between the second and third line, so about here, we would have another x-intercept because the gradient of the original function is 0. So our gradient function's y value, f prime of x, will equal 0. Awesome. And actually that's kind of all we need, because we know it's going to be a positive quadratic. So between these 2 points, I can sketch a positive quadratic, like so. Now let's just double check, make sure this makes sense. So looking at the original function, so to the left of the maximum, this gradient is positive, right? It is increasing, it has a positive gradient. So our gradient function should have a y value above the x-axis, right? Which it does. Similarly, after the minimum, the gradient is positive, right? Which means our gradient function after that x value should have a positive y value, right? A positive f prime of x, a positive gradient. Now, between the maximum and the minimum, the gradient of the cubic is decreasing. So on our gradient function, we would expect the y value, which represents the gradient, to be below the x-axis, right? Which it is. And again, those turning points, the max and the min, will have a gradient of 0, which is how we got those x-intercepts in the first place. Alright, and now I guess a question for you is, where does this cubic have the steepest negative gradient? So looking at the yellow section, that's all the negative gradient. And where is that steepest? Right, it's steepest in between, like exactly in between the min and the max. So just eyeballing it, maybe around here. And so on our sketch, the most negative gradient should line up with the vertex of our quadratic, right? Because that is the lowest y value, which corresponds to the most negative gradient. Right, at that point, it's the steepest. All right, and so for this question, if we got the x-intercepts in the right position and we drew a positive parabola, we would get achieved.